This is Mengqi Zou's lab5 report. This is the structure of this lab report. In this lab, we want to record the average time of the 5 throws of the bar magnet falling down a tube, and also use the computational model to simulate the whole process. Those are the results. These are the fundamental physical principles in this lab, and I will introduce how to utilize them in detail in the following sections. Firstly, I determine the north end of the bar magnet by using the magnetometer app and record the whole process of dropping the magnet through the tube, which is made by the roll of aluminum foil. I calculate the time it took the magnet to fall through the length of the tube and repeat this experiment for 5 times and calculate the average time. I also measure the mass of the bar magnet, length and inner radius of the tube, and the width of the aluminum foil. Those are my measurements. And we come to the computational model section. Firstly, I calculate the magnetic field at a position R to a bar magnet. According to Biot-Savart law, we can get the equation to calculate it. And this is the code to calculate the rate of change in the magnetic flux through each ring caused by the falling magnet. And then I use the Faraday's law to calculate the current induced in each ring by the falling magnet. According to Faraday's law, the EMF is equal to the negative rate of change of the flux. And we also know that EMF equals the resistance times the current, so that we can get our equation. And then I use the Biot-Savart law to calculate the force exerted on each current carrying ring by the falling magnet. We know the equation to calculate the force exerted on the loop, which is IBL, and we also know the Faraday's law and Biot-Savart's law. Thus, we can get our final equation to calculate the force exerted on the loop. And also, according to the Newton's third law, all forces between the two objects exist in equal magnitude in opposite direction, so that we can know the magnetic force on the loop is equal to the magnetic force on the magnet. And then we can calculate the net force exerted on the magnet, and according to Newton's second law, we can find the formulas to find the velocity and position of the bar magnet. And this is my final result. The flux is increasing downwards due to the increasing magnetic field of the falling magnet towards the rings. And the magnetic field of the induced currents should be upwards according to Lenz's law. According to the right-hand law, the current should be counterclockwise. So blue color represents the counterclockwise and the red color represents the clockwise. When the magnet is flipped, the direction of the rate of change of the flux also flipped. So the direction of the induced currents also flipped. And my experimental value is 0.29 second and the computational value is 0.34 second. We can observe that they are actually close to each other, and the small deviation is due to the error when videoing the falling bar magnet. And from the graph, we can see that as the velocity decreases, we know that the bar magnet decelerates. According to the Newton's second law, F equals ma, we find that the two forces are actually trying to cancel each other. For the reflection questions, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling bar magnet change? Because the current equals the EMF divided by the resistance. As the resistance becomes very small, the current will become very large. And for the second question, the induced currents in the magnetic force will decrease. As a result, the bar magnet will fall much faster. In conclusion, by using the glow script to simulate the bar magnet falling down a tube and applying fundamental physical principles like Faraday's law, Lenz's law, Newton's law, Bioservice law for calculations, we finally can get the results.